In today's video, we are going to solve a problem relevant to heat convection, and we are going to see some application of Newton's law of cooling. So without further ado, let's begin. So the problem says that there is a cartridge electrical heater which is shaped as a cylinder of length L equals 200 millimeters, and the outer diameter of the cylindrical shaped cartridge electrical heater is 20 millimeters. Under normal operating conditions, the heater dissipates 2 kilowatts and it is submerged in a water flow that is at 20 degrees Celsius and provides a convection heat transfer coefficient of H equals 5000 watt per meter squared Kelvin. Now if we neglect heat transfer from the ends of the heater, then can we determine the surface temperature Ts? And the question also asks, if the water flow is inadvertently terminated while the heater continues to operate, the heater is exposed to air which is also at 20 degrees Celsius but for which H equals 50 watt per meter squared Kelvin, and then what would be the corresponding surface temperature and what would be the consequences of such an event. So basically we have to do this problem twice, and in the first case the heater is submerged in a water flow and we know the temperature of that water and we know the heat transfer coefficient of that water and heater surface, and then we can apply Newton's law of cooling to solve it. And we are going to basically repeat this process by assuming that for some reason that the water flow is suddenly stopped and now the heater is only exposed to air, and because the working fluid has changed, now the heat transfer coefficient has also varied from 5000 to 50. So it has decreased by a factor of 100. So in that case, what would be the corresponding temperature and what would be the consequences of such an event? So let's solve this problem. So we have drawn the sketch of this problem, and basically this cylinder represents the cartridge electrical heater, and we know the length of this heater, we know the diameter of this heater D, and from that we can actually get the surface area AS equal to pi dl of this heater. So we are going to make some assumptions before solving this problem, and during this assumption making process we are going to simplify this problem. So let's make some assumptions to solve this problem. So we make the following assumptions to solve this problem. We assume that the problem is solved under steady state conditions. So the temperature anywhere on this cylindrical cartridge heater or the fluid that is around this cartridge heater, the temperature of these two things, or to be precise the bulk temperature of these two things, they do not vary with time. After that we assume that the surface temperature is uniform. So anywhere on this surface, that is I am marking with red color on the cylinder, is uniform. So that temperature is the same at every single point. Otherwise we cannot use Newton's law of cooling. We also assume constant thermal properties such as the thermal conductivity or heat transfer coefficient is constant, it does not vary with time or does not vary with temperature. We also neglected heat transfer from the ends of the heater. So there are two circular ends, one is this end and another one is this end, that I am marked with red crosses, and there are no heat transfer from these two ends. We also assume that the sole heat transfer mechanism that is present in this problem is heat convection. So there is no radiation or no conduction heat transfer is going on, so they are neglected. We also assume that all the electrical power that is generated by this heater is transferred to the fluid. So whatever the fluid, if it's water or it can be air, so whenever it's transferring to water, all the electrical power generated by the heater is transferred to the water, or when the heater is surrounded by air, all the electrical power generated by the heater is transferred to air by only heat convection. So the assumptions number 5 and number 6 are made to simplify this problem. Since we are interested in surface temperature, we can simply write it as follows. We can write Ts equal to Q over HAS plus T infinity, and we can further simplify it by writing Q over H pi dl plus T infinity. So we actually know the value of all of these quantities under different conditions, and from that we can actually calculate the surface temperature of the heater when it was submerged in water or when the water flow was terminated and it was submerged only in air. So let's try that. So let's do it for water. So in water we can actually write the surface temperature for the case of water being surrounding the cylindrical heater, and write TSW equal to QHW by dl plus T infinity, and we can put the values. So Q is 2000 watts because it was 2 kilowatts. HW is 5000 watt per meter squared Kelvin. Then we have pi, which is 3.14159. Then we have 0.02 meter. It's because of the diameter being 20 millimeter, and the length was 200 millimeters, so it is 0.2 meter. And the temperature of the water was 20 degrees Celsius. So we can also write that. So by solving this, we would get 51.8 degrees Celsius. And similarly, we can solve this equation again, but this time we are going to do it for air. So in air, we can write TSA equals Q over HA by dl plus T infinity. Because other than this H, everything remains the same, so we can just quickly write down all those values. So the H becomes now 50 times pi times 0.02 into 0.2 meter. So just to keep things simplified, I'm just going to erase this unit because I know the final answer is going to come out in the form of a unit of degree Celsius. So I'm going to just write that. So if we solve this, we would get 3203 degrees Celsius. So from this, we can clearly see that when the heater is surrounded by air, the temperature is much higher. So these are the two values the question actually asked us to solve for. So we got our answers, that what would be the surface temperature, but the question also asked what would be the consequence of such an event. So if suddenly water flow is terminated, the surface temperature of the heater would rise from 51.8 degrees Celsius to 3203 degrees Celsius, which is very high, and it's going to melt the heater surface material and damage the heater or cause the heater to fail. So from this, actually we learned that there are two very important lessons that we can actually take away from this. And the first one is that actually air is a very poor fluid. Air is a very poor heat convection fluid because it does not take away that much heat from the surface, and it's going to cause it to melt. And we also have to correct one of our assumptions. So when we started to solve this problem, we assumed that radiation heat transfer is negligible, but since we have solved this problem, particularly when the cartridge heater was surrounded by air, we noticed that this temperature value became very large, and from the radiation heat transfer law, or Stephen Weinberg's formula, we know that the heat transfer due to radiation is proportional to the fourth power of temperature. So from this we can actually write that we initially assumed that the radiation heat transfer was negligible, but in air at high temperatures radiation heat transfer is not negligible, right? At high temperature radiation heat transfer is not negligible. So that's the solution of this problem. From this problem we learned how different fluid fluids behave during different convection cases, and from this we can design equipment safely. I hope this solution was useful to you. Thank you for watching my lectures.